You spent God knows how long in the last month, with logic and simplifying logic and all that, and it's just a real pain. It's not how we do it for real. So we're going to show you today a much better way to simplify your logic. It'll make your life a lot easier. Okay. So basically, these are Carnot maps, K-maps, and the way they work, they're based on one simple logic property. Okay, and it's the combining property. Okay, and what this says is that x and y plus x and y not equals x. Okay, does that make everybody remember that? That was one of your logic properties that you remembered. So if we draw, we'll call this function f. Okay, so we see what happens if x is 0. Well, then this term is 0 because x is 0. This term is 0 because x is 0. And this is 0. If x is 0 and y is 1, they're still both 0. If x is 1 and y is 0, that means this term is 0, 1 and 0, and this term is 1 and 1, so it equals 1. And then if both of them are 1, we have a 1 here or a 0 here, which is 1. So as you can see, x is replicated at the output. So this is not only true for x can be any collection of terms. So if we have a, b, c plus a, b, not c, that just equals a, b. Okay? So this is the property that we're going to exploit in order to simplify our logic. Okay, these are the different dimensionalities of K-maps. We generally do them in 2 dimensions because it's easier for us to visualize. We're used to seeing things on paper in 2 dimensions, so it's the easiest way to write them. And as we'll see as we go along, it's also easier when it comes to simplifying the expressions. So this is a 2-dimensional K-map. Here we have our x, here we have our y. Then we would go in, and if we have, say we have x and y, and we want to put this on the K-map, we know that this is 0, 0, 1, 1, 0, 1, 0, 1, and x and y is 0, 0, 0, 1, right? So that means that all of these get 0 except where both are 1. So y is 1, x is 1, so that is 1. So we're going to see how this relates to the other dimensionalities. Now in 3 dimensions, this is 3 dimensions. We put 2 of the dimensions along one axis and the 3rd dimension along the last one. It can also be, as Sam pointed out, can be done as a cube, but once again, it's not quite as intuitive. It's another way to think about it. We're basically compressing 3 dimensions down into 2-dimensional space, so it's easier to manipulate. Okay, so let's do. The cube shows the wraparound very clearly. That's true. That's true. So let's do an example here to get a understanding of what's going on and how we go about manipulating these things. So we're going to define just an arbitrary function. Okay. Okay. Okay, then we're going to do 0, 1, 1, 0, 0, 1, 0, 1. Okay? Now, we could go ahead and write a logical expression for this truth table by doing either a sum of products or product of sums, right? We all remember that from last month. And so we would do something, it would be something, you know, not x, not y, z, or not x, y, and z, or, and then just going along. So it would be, for every one, if we were to do a sum of products, every term here would basically be a triple and then it would be, so that you would have 4 of those terms and they would be ORed together. So in terms of logic, that's pretty complex. We would need something, you know, we would need something like this.
What's the logical condition you're using here for f?
It doesn't, it's arbitrary. We're just,
So you just filled in arbitrary numbers
yes.
below it?
So it represents some function, okay? So in order to implement this, we would need to do something like this. So, and this would each of these would have 3 inputs. Okay. Now, from a circuit's perspective, that's a lot more. I mean, as we know, you know, it's expensive. If you're designing an integrated circuit, if you're designing a logic to go on a chip, the real estate is very expensive. You know, every time you do this, you know, you might make millions of these chips, and if you can save space, it's going to save you probably millions of dollars to reduce this from four gates with 3 inputs and 1 gate with 4 inputs to something simpler. So this is how we're going to do that. So let's go ahead and fill in our K-map. Generally, we only fill in the 1s or the 0s because we're only going to work with the 1s and the 0s. We'll start out working with the 1s, and at the end I'll show you what we do with the 0s. Okay, so we go not x, which is not x is this region. Okay, then we do not y. Well, not y is these 2 spaces, and z. So we 0, 0, 1. So 0, 0, 1. Okay, so we put a 1 there. Okay, then we go to the next one. 0, 1, 0, 1, 0, 0. So we put a 1 there. And we keep filling in, and we get a 1 there and a 1 there. Okay? Now, what we do, the next step, is we draw a circle around our adjacent 1s. Okay? So this 1 is by itself, so it gets a single circle. These 2 are next to each other. Yeah, but you only put 2. You only put them together in twos or in blocks. Yeah,
between choosing the 2 that wrap around.
well, we're also gonna circle that one. Okay. Okay. So that's all well and good, but what the hell does it mean? Well, let's think about it. So these 2. Let's look at these 2 values. So this one is x, y, z, and this one is x, not y, z. So we have x, y, z, and plus x, not y, z. Well, according to our combining property, we can go ahead and just simplify this to x, z. So we'll draw a little line here and say, okay, this circle here simplifies. We can simplify both of those terms into x and z. Okay. This one, well, it only has 1 around it, so there's not much simplification we can do. So we just have to write this one as not x, y, not z. Okay. And then there's this last one here. Well, let's start, instead of doing this every time, let's start to be a little smarter and look at what's going on. We've drawn these brackets in here so we can see which, when we look at, let's look at this one. So this stays not y for both of them. It stays z for both of them. But x. X is 1 here, so it changes from x. So we're going to eliminate the x in that expression. Everybody get that? Are you okay? So if we eliminate the x from that expression, it becomes not y. Not y and z. Okay? So our new expression then is So our new expression is f equals x and z plus not y and z plus x, not x, y, and not z. So this here is equivalent to this, which would have been the, you want me to write out the four terms that it would have been to show you what we've simplified, or? Okay. So it would have started out to be f equals x, y, z, not, plus x, y, z, not, plus x, y, z, not, plus x, y, z. So we've taken this expression and simplified it to this expression. Whereas we would have had to implement this logic in order to implement this function. Now we have simplified it down to a situation where we only have 3 of these gates. And 2 of them only have 2 inputs. So we've gone from 4 gates to 3 in this layer. 2 of them only have 2 inputs. 1 of them has 3 inputs, and then we only need a 3 input OR instead of a 4 input NOR. So our logic has been, we've simplified the number of gates. We've simplified our logic. It's a much easier expression to understand. Okay. So let's do a little more. Let's get a little more complex then.
Could you also see? I think I see, but could you also see that it's the whole row Z except for the single exception, and build a circuit out of that?
This actually gives you the minimum number of gates that you can build your circuit in. So it doesn't. When you have a method that is this easy, it's kind of no reason not to. Right. So we're gonna do another function here. Let me erase my. Okay.
Using only these 3 gates and not gates like XOR or something like that.
Right, right. So let's do another function. So f equals xyz plus xyz not plus xyz not plus xyz not plus xyz not. Okay? So I'm just going to go ahead and put the values into the table. If you went through, we would come up with 1, 1, 1, 1, 1. Okay? Well, now this presents an interesting opportunity, because now we have a foursome instead of just a duple. So we can now draw a larger block here. And then we'll also draw this one. Okay? Now what is well, we know this one, so let's do this one first. It stays the same in x, it stays the same in z, so it changes in y. So we eliminate y. So this becomes x, not z. Okay? Now, for our four tuple, it's a little. Let's think about what this is. Well, which way do we want to simplify it? It changes in z, but it also changes in x. Well, so if this property holds true, regardless of the number of variables, we could simplify it in terms of z and eliminate the z, and we'd have this and this. But then we can also simplify it in terms of x. So basically this four tuple simplifies to just y naught. Okay? Let me say that again. So if we simplify this, we can simplify it by eliminating the z dependence. At which point it becomes this set, which is not x, not y, not z. And this set, which is yeah, let me, so it's x, not y, not z, right? Okay? Now, these are the same, so that we drop those out. So this is x, not y, and this is x, y. And then we can go ahead and eliminate the not x's, and it just becomes not y. Does everybody understand that? Get that?
You can see it visually too.
Yeah, I mean that's one of the good things about this is it's a very visual technique, and it lends itself. It's almost better to look at it and understand it than it is to write it out. Okay, so that's how we would go about when we have a block like that. So our final function then becomes
the one up there that was not part of the for tuple. Isn't that going to be in a sense counted twice since it's
Yeah, but
the rightmost one? Is
yes, but it's a
not y.
it doesn't matter. It's a 1.
1 or 1 is just 1.
Right.
It's a logical
Okay.
addition.
Okay. So our function.
But you also could have done it. Not y and x, y, not z. You didn't have to make a double circle for that.
Can you go over again visually how you see it? So
Okay. So we have these brackets here, right? Okay. So those brackets tell us where each of our variables doesn't change. Okay. So basically, if our circles cross those bracket lines for a particular variable, that means it changes and we can eliminate that variable. So when we have the for tuple, we see that when it wraps around here, that it changes x, it changes z, right, this way. So that means the only variable that doesn't change is the y, which in this case is y naught. So that's how we get y not y for that. So we've simplified. Yeah, question? So this expression here, which we would need 1, 2, 3, 4, 5 triple AND gates and 1 5-input OR gate, we've simplified to something that you need, basically an AND gate and an OR gate. That's quite a simplification. Andrew, do you have a question?
I figured
Okay.
Now,
Why wouldn't it just be x plus not 1? Because all the x's are lit up, right?
no,
No.
You erase that one.
Oh,
that actually looks like
oh,
x and z is not.
Erase the-
okay.
You did have one there.
Which,
0.
There's a little, no.
that one? Oh, this. Okay. Okay. So,
Now, we also could have done x, y, not z, plus not y. Is this
x, y, not z.
Put the circle around
just
that
put the
one.
circle around the outstanding?
Yes, we could have, but then it wouldn't have been the most simplified, and it would have. Right. Right. Okay. So you comfortable with that? Let's do something a little more complicated. Let's move to the big one. Okay.
From an algebraic point of view, x dot y plus x dot not y equals x times y or not y in parentheses, which is x or true, which is x.
Right.
So we can simplify. If we don't want to think what it means, we can simply play games with the algebra.
Yeah. Yeah. This is it's basically a graphical representation of the algebra. A lot of people find it more easy to work with the graphical. Some people find it easier to work with the algebraic expressions. Some people find it easier to work with the graphical expressions. So let's do a big one, okay? And in doing this, we're gonna define some new things. First, let's define our function. We're gonna define our function in kind of a new way because it gets to be a pain to write out. So we're gonna define it as the sum over w, x, y, z of 1, 3, 4, 5, 9, 11, 12, 13, 14, 15, right? So basically what this means is this is the WXY. So this is 0, 0, 0, 1. This is 0, 0, 1, 1, and so on. So these are basically just the expressions. So if you were to actually write out the logical expression, you would have 1, 2, 3, 4, 5, 6, 7, 8, 9. You would have 4, 4, well, you would have
10 4-input AND gates.
10 4-input, yeah, thank you. 10 4-input NAND gates and then a 10-input OR gate afterwards, right? So that's something that's definitely worth simplifying, right? So let's
Go over the 1, 3, 4, 5, 9.
okay, so each one of these numbers represents a WXYZ, okay?
So we don't know which.
You translate it to binary. So
Oh.
this is 0, 0, 0, 1, this is 0, 0, 1, 1, 0, 1, 0, 0, so on, okay?
Now that makes sense. Yep.
Okay.
And I'm just curious how you, to generate those numbers, would you go through and first have to look at all your combinations of W, X, Y, Z? Or,
What do you...
I mean, why isn't there a 2 or a 6 or a...
It's just an arbitrary, it's an arbitrary logical function, okay? Doesn't necessarily mean anything. Okay, so let's put this on our K-map. One thing to notice that I didn't explicitly point out was that the way we labeled our axes, you notice it's 0, 0, 0, 1, then 1, 1, and then 1, 0. Why did we do that? Gray codes, right, exactly. So that we know that we're never more than 1 bit away, which is why we can use the combining property when we do it that way. Okay? So if you wanted to do a six variable thing, you would write basically along here the gray codes for 3 bits, right? Okay. So let's write down fill in our K-map here. Okay. Pretty full. So let's start circling things. We will in a second.
Okay.
All right. So we have all those, but we see something here. We see that this line across here is covered in this here, and this here, right? So the line here isn't really necessary. So we're going to define some things here. So anytime we draw a circle around a group of numbers in here, we call that a prime implicant. Okay? So this is a prime implicant, this is a prime implicant, this is a prime implicant. Okay? So each one of the circles we draw defines a prime implicant.
What do you mean by prime?
It's a single set of numbers. It's when we circle this is a prime implicant. Okay? It's the set of numbers that we are circling to simplify that lends itself to simplification because of the way we've defined our K-map. Okay?
It could be any power of 2.
Yes. Yes.
Do you have this set also that wraps around from the right side to the left side of square of 4?
Oh, no, I don't. That's a...
So,
Yeah. You're right.
Couldn't circle 6.
No.
Okay.
No. Has to be a power of 2. Okay? Now we're going to define something we call distinguished one cells. What a distinguished one cell is a cell with a 1 in it that is only covered by 1 prime implicant. Okay? So in this case, this is only covered by this square. So that's a prime implicant. Or that's a distinguished one cell. Then we have
And bottom second.
actually I did this just a little. Because we drew that, we don't have the one here, so let's become that and that. Okay.
So I guess the rule is always the bigger circle the better. Right?
Yes. So this is a distinguished one cell. This is a distinguished one cell. I think that's it. Okay. Now, what we say then is that we have to the distinguished one cells.
Why would 0011 be distinguished? Because
This one.
Yeah, because you can make a circle going off the left side of the board and coming back on the right side.
It's included in this. It's included in the 4 tuple. That is that prime implicate is a subprime implicant of the 4 tuple. Okay. So what we then say is the prime implicates that include these distinguished one cells we call essential prime implicants. What we mean by that is we have to have those prime implicants included in our logic expressions. Okay. Now in this case we look at this and we say, okay, so that means we need this square. So let's as we go through, let's check these off in a different color. When we've covered a square, we're going to make just a little blue mark in it. Okay. So by doing this, we need this because this is an essential prime. This is an essential prime implicant for the distinguished one cell. So we know we have this. We know we have this. We know we have this, and we know we have this, right? Okay, we have to include this here because this is a distinguished one cell, and this is its essential prime implicant. So we cross these off. And this one, means we have to include this. So we cross.
Why all 4 and why not just the 2?
Better to use 4 than
It's because it's better to use the 4 than the 2.
You get rid of the negates.
Okay? So, without ever using this one that goes all the way across, we have covered all of the numbers in our K-map. Okay? Does that make sense? So let's go ahead and let's do some simplification. So let's simplify this one right here. So this stays the same in W. It stays the same in X. It changes in Y, right? Covers all 4, so it changes in Y. And it also changes in Z. Okay?
Could you just back up and restate the rule you stated before you put the blue X's?
The essential prime implicant rule?
Yeah.
If a distinguished one cell is part of a prime implicant, that implicant is called an essential prime implicant. So an essential prime implicant is a prime implicant that contains a distinguished one cell. And what that means is that we have to include that, because if we don't, we have to include that term in our final logical, simplified logical expression, because if we don't, we'll be missing the representation of the distinguished one cell.
Okay, and so therefore you identify those first, and if that takes care of all the circles, then you're done.
Right. Okay? So we start defining. So this stays the same in W, stays the same in X, but it changes as we look at this axis. So we're doing this one right down here. It changes in Y and it changes in Z. So this one right here simply becomes W and X. Okay? So now let's do this one. So this it wraps around, which means it stays the same in X. Okay, but it changes in W. So let's do them in order. So we'll start with W. Does it change in W? Yes. So we eliminate W. Does it change in X? No. So we write down not X. Does it change in Y? So up here, here's Y. So we ignore Y. Does it change in Z? No. So that's our logical expression for that. And now we have one more, which is this one right here. And does this one change in W?
Yes.
Yes. So we don't write down W. Does it change in X? No. Does it change in Y? No. Does it change in Z?
Should be not like
Oh, yeah. Sorry. Does it change in Z?
Yes.
Yes. So our final logical expression is W and X, or not XZ, or X not Y. Okay? So we've gone from a situation where we had 10 4-input AND gates and one 10-input OR gate to a situation where we have 3 2-input AND gates and one 3-input OR gate. So that's quite a simplification, right? Okay, so let's do one more. Question?
Is there a difference? It seems like this essential rule thing just says we get rid of a redundant one.
Exactly.
If it doesn't have one of these essentials or whatever it is, then it's entirely redundant.
Yes, but you do have to be careful though, because something can be redundant, but not included in not a distinguished one cell. So you have to be careful. So if we have a situation, let's not think about the map, but let's look at this. Okay, so we'll have something like this. Okay, and then say there's another one here, so we have this and this. Okay, these two aren't distinguished, but we can. So the distinguished one cells in this case are here and here, right? So if we just did the essential one cells, we would just do this group here, or the essential prime implicants would only be here and here, but we have to include these two somehow. So that's something you have to be careful of when you're simplifying these expressions. Does that make sense?
Yeah. So what is the rule really?
The rule is be careful. Exactly. Make sure that you do your essential prime implicants. Mark off, mentally mark off what you've covered, and then if you haven't covered anything, then you have to pick things that cover that.
Basically saying they're necessary, but not necessarily sufficient.
Exactly.
Yeah.
Yes.
But how do you then pick the rest? I guess that must be
You just pick.
So suppose the rest is fairly complicated.
You have to choose what looks to be best. I don't have a
bet.
bet.
Then you perhaps start with the one that's covered by 2 cells.
Yeah.
Go out like that.
So what would you pick for that little staircase?
Well, I could include, to cover both of these, I could include this and this, or I could just include this.
That seems better.
Well, this gives me, if I pick these two, that gives me 2 different logic expressions, which is 2 gates, which is another input to my OR gate. So I would pick this because it's a single expression, only adds 1 input to my OR gate then. Okay? All right.
You know with that bottom distinguished cell?
This one?
Yeah, you chose to do all 4 instead of just 2, and you said it's better to do that?
Uh-huh.
And I'm just confused why, because if...
Well, in this case, it's always better to cover as much area as you can.
Even if the 2 have already been accounted
Yes.
for.
And why? I like.
Well, because if we had simplified that to just that,
Yeah.
this would have had 3 terms in it. So it would have changed only in Z, not in X, W, X, or Y. So by covering that, we eliminated another term, another input to our AND gate. Okay?
If this is a sum, could we just work it through and produce out a result?
What do you mean?
The purpose of this is to sum that series.
Well, this represents a sum of products.
Yeah.
So, W, X, Y, Z, not, plus W, X, not W, not X, Y, Z. So it's a product. It's a sum of all these products, right? So each one of these represents a product, right? Mm-hmm. So it's a sum of all these products. Does that make sense?
Yes, what I'm asking is if that can be expressed either in binary or in decimal.
It's a logical sum. So we want to provide that functionality to, we want to build in some, say we want to build a circuit that reproduces that functionality. It goes back to starting, what I didn't show here was, starting with a truth table, starting with a big 4-input 16-bit truth table, and, doing the outputs, and then basically all that information is in here. Okay? Does that make sense?
I think it's another use
Yes,
This is just a-
I realise that. I just wonder whether there's any way to get to it.
Right, but
whether there's some relation.
No,
the
they're
use of the notation, I think, seems
yes,
very different.
or they're orthogonal. They don't cross, or they don't interact with each other. The two uses there. Okay, so moving on, we're going to do one more, then we'll move on to something else. Okay, so our logical function that we want to implement, we're going to express it the same way. Is 2, 3, 4, 5, 6, 7, 11, 13, 15. Okay, so I'm just going to fill these in. I'm going to go through this one rather fast because what I really want to show you is what we're going to do after this. So just follow along. Okay. So now we find our distinguished one cells. Right? All right. Okay. So now let's do our simplification. Well, this doesn't change in W. This does change in X. Doesn't. So we have not W. Doesn't change in Y. So this is Y, and Z does change in Z. So this one right there is not W, Y, right? So then let's do this one. This one doesn't change in W. X doesn't change in X. Does change in Y. Does change in Z, right? All right. When we do this one doesn't change in Y or Z, but it changes along X and W. So this just becomes YZ. And lastly, this one here, W changes in W, yes. Changes in X, no. Changes in Y, yes. Changes in Z, no. So now we've simplified our logical expression to W, Y plus not W, X plus XZ plus YZ. All right? Great, fabulous. We did a great job. Question?
Couldn't you reduce it to like 3 expressions by doing a not?
Yeah.
Like do the zeros, like you'd be.
That's what we're going to do next.
Okay.
Good thinking. So, as I said, we can do either the ones or the zeros, and in some cases, we see that we'd only have 1, 2, 3, 4, 5, 6, 7. We'd only have 7 zeros, and they would be arranged such that it would be pretty easy to group them, right? So let's do our zeros. So. Yeah, that's what I need to do. Okay, so our zeros, so this can be expressed as this, as a sum of products. But if we went ahead, we could also express it as the product of sums, right? And what you do in that is you just, as this goes back to last month, you look at the zeros instead of looking at the ones. So we see that that expression basically becomes. Have you guys seen the symbol?
No, I can't see it.
Whereas the sigma is a sum. This is a product. So this is multiplying the terms together. So we basically have in our product all the terms that we don't see over there. So we have 0, 1, 8, 9, 10, 12, and 14. Okay? And so this represents a product of sums. A product of sums output. So let's draw our zeros in. Now let's draw our circles. Okay. Now let's define our distinguished one cells. Actually, that one doesn't. This isn't a. So this is a distinguished one cell, and these two are distinguished one cells. So we have three groupings, or we have two groupings, right? We have this that wraps around here, and this that wraps around here. So we can simplify this. So when we write, so this changes. Does this change? So we're going to write this instead of a product. We're going to write it as the sum of the inverse of the variable. Okay?
Should the location also be a distinguished cell? Yeah.
Shouldn't what? Oh, yeah, yes. You're right. So let's look at this. Let's look at this term right here. Right here. This right here. So it doesn't change in W, right? And it's W, so it becomes W naught. Plus, does it change in X? X, yes, changes in X. We eliminate X. Does it change in Y? Yes, changes in Y. We eliminate Y. Does it change in Z? No. So if that's a not Z, so it becomes plus a Z. Okay? Then we do the other one. Same idea. Does it change in W? Yes. Eliminate W. Does it change in X? No. So that's not X, so it becomes X. Does it change in Y? No. It's a not Y, so it becomes a Y. And then Z, it does change in Z. All right, so our function is then W, not W, plus Z, and X or Y. So by doing this, we've gone from two input ORs and one two input AND from where we started, which was 10 4 input ANDs, one 10 input OR, down to this situation where we have two input ORs and one 2 input AND.
Did you cover the
But we
two
could have.
symbol?
We
I
could
think you
have
missed the.
The two symbol?
It's already
It's already covered.
We could have eliminated that whole
right.
picture by simply factoring this.
We could have what?
We could have eliminated that whole picture by just factoring this.
Oh.
We could have.
Ry times x plus y.
We could have.
Plus z times x plus y, which is this.
But it won't always be that easy. I mean, this is a simple example. When you get to larger dimensions and more spaces,
Like it graphical.
So
One or the other.
that was your introduction to K-maps. Any questions on K-maps? Yes.
How many circles did you use in this one?
2.
Just 2?
We used. So one started here, goes around, wraps around, comes up here. And then this one wraps around here. Okay?
So you have to do both of these and see which one is smaller to get the guarantee of the smallest?
Well, when you put, you kind of can develop an intuition. Okay? When you start to put your values on your K-map initially, you can kind of look at it and decide, you know where your ones, when you put one of them on, you know where the other one is, right? So you can kind of look at the cells filled with the ones and say, well, how many circles will I need to cover the places where are ones? Well, how many circles will I need to cover the places where there aren't ones? And you can go with either that you think is going to be better. It's kind of developing some intuition about drawing your circles and what covers the most area and things like that. Okay.
Can you notice that there are more in that sum than in that product? Is that a general?
No, because it depends on the placement. It depends on the placement in your K-map.
What's the application where you have to develop circuits for these arbitrary functions? Does that come up with that?
The control logic for the beta. So you have a whole bunch of logic that all it does is it sets which PC you're going to take. Are you going to take the PC that comes from PC plus 1? Are you going to take the PC from the ALU that's computed by a branch instruction? You have a lot of arbitrary logic. Usually you don't sit down and define, I want to do this logical function. Usually you have something that you want to control, something that you want to do, and you have this huge, truth table, and then you go ahead and you say, okay, great, now that I've got that, I want to build a circuit. How do I go about that? And that's where this comes in. Although it does lend itself also to more standard logic designs.
And these circuits are right on the chip.
Yeah, or you can build them discretely. Either way. I mean, if you were going to Radio Shack and buying gates to implement these circuits, wouldn't you want to buy the least number of gates that you had to? Okay. So, let's talk a little about adders. And then if we'll have time, I'll show you a little bit about multipliers. Okay. So you guys... So you guys did I assume that the ripple carry adder was pretty okay. Were you guys okay with that? If that's the case, then I'll just go on and start talking about the carry look ahead adder, which I imagine is what probably gave you more of the troubles. So we know for our adders that sum equals A or B or C I, right? And we know that the carry out equals A, B, or B, C, I, or A, C, I, right? That's pretty well established. Well,
is that an XOR symbol up top?
Yes.
You're neglecting the case where it's A and B and C?
No.
No, AX or B, X or C is also
If
true.
A and B.
Let's look at let's draw the truth table real quick. Ah.
Oh, okay, right.
So this is 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 1. Okay? So we kind of break these up into a couple different categories. So let's look from here down. We notice that if A and B are both 1, regardless of what Ci is, that CO is 1. Okay?
Please put the S column to the right of the C0 column. Then it'll be crystal clear to everybody.
Oh, you want me to move that one? You want me to?
To the right of the C0 column.
Is that how we did it yesterday?
No.
I bugged the heck out of Sam then too.
Sam, just for you.
It'll be crystal clear to everyone else.
So 0, 1, 1, 0, 1, 0, 0, 1. Okay?
If you view that as
output
binary digits, it's 0, 1, 1, 2, 1, 2, 2, 3, which is exactly the number of ones in A, B, and C.
Okay.
Can someone lower their head for just a second? Nice, thank you.
So, if we look at A and B, we see that if A and B are both 1, that C out is 1 regardless of what Ci is. Okay? Doesn't matter what Ci is, C out is 0. So we call this case generate. So when A and B, then C out equals 0. So let's define. We're going to define. This is where we define our new functions. We define generate as A and B. Okay? Pretty simple, because whenever there's an A and a B, we know that we get a carry out. Okay? Now our next function is called propagate. And basically what propagate does is it looks at our carry out and says, okay, when do we propagate? So if we have a 0 and a 1 in A and B, regardless of the order, then we see, so let's draw a line here. Then we see here that the carry in just propagates to the carry out. Okay? Everybody get that? So we know that if A XOR B, then we just propagate our carry in to our carry out. Okay, so we call this function propagate. The generate says whenever A and B are both 1, carry out is 1 regardless.
So right now these are both things for the carry out.
Yeah, and now we're going to define our sum and our carry out in terms of these two functions. Okay, so we can see that carry out as a function of G and P equals, well, if we generate, we definitely know that there's a carry out is true, right? So we know G, right? And now we know that if propagate is true and carry in is true, that carry out is true, right? Does that make sense to everybody? So we say P and Ci. All right, so that's what our carry out equals. Now our sum, as a function of G and P, equals, well, we see that P is A XOR B. We know that S is A XOR B XOR Ci. So we can just do P XOR Ci. Okay? Now, you may say, well, great, we've defined these functions, but they represent the same thing. What good have we done? Here's where the interesting part comes in. So we have our carry out. So let's write our first carry out, C1. It equals generate 0 or P0 C0, right? So what this basically says is that when we're looking at a multi-bit adder, and we're going to calculate C1. Okay?
Carry out backwards.
Yeah, that's carry. Ci is what?
And C0 and 1 and not I.
Oh, I see.
Okay. So then we can write our second carry bit as G1 plus P1. So this is actually C. Yeah, this is C0.
Which is always false.
Not always, but usually. There are situations, I mean, if you have an overflow bit coming from somewhere else, it might not be. So then times C1. Okay? But this, we know what C1 is, right? So we can go ahead and fill this in recursively. Okay? And then if we'll do one more, equals G2 plus P2 C2, which equals G2 plus P2 times G1 plus P1 times G0 plus P0 P1 C0, which equals finally G2 plus P2 G1 plus P1 P2 G0 plus P0 P1 P2 CO. So as we can see, we can go ahead and write this recursively. Well, that means if we have our A's and our B's, we see that the only carry out signal that comes into this is our initial carry out, right? Our C0. So if we have, when we design adders, I mean, we assume that all of the inputs from the last stage are available at the same time. So all our bits for A and all our bits for B are available, and our carry that's coming in is also available. So that means that we can then figure out what the carry in for any bit in the sum that we want is by having all of this data. So we have all our A's, we have all our B's, we have our initial carry bit that comes from wherever our data is coming from to be added, right? And it's all available at the same time. So what we can do then is implement something like this. You guys seen this? This is the symbol for XOR. So we'll call this XI and YI. Or maybe it's better, we'll call it A and B. Probably easier. AI, BI. And then we have and then down here we have this magical block. And this is our carry look ahead logic. Okay? What gets input to that? Well, A0 to AI minus 1, and then B0 to BI minus 1, and then C0. So then the output from this comes here. So this is your carry in bit. This is your AI XOR BI, and then this is your SI. I see a lot of blank faces.
You saved a fortune in time, but the electrical engineering inside that black box is enormous.
Yes, which is another problem, right? So this is great. This is great. However, if you do this, let's look at a.
Okay, can you go on that circuit again?
Yeah. So we have our A XOR B, which is, as we defined here, is our propagate. So we have propagate, and then we did our carry in with all that logic, all the carry look ahead logic there, right?
That
Which was
box is just that stuff.
Yeah, it represents basically implementing this recursive equation. So we input all our A bits, all our B bits, and our CO bit. Okay, the first carry bit that comes in, and from that, using these equations, we can generate our CI bit for that stage. Okay, so the sum is generated. So then you have your A XOR B, which is your propagate, and then you XOR it with your CI, which gives you the sum. Okay, does that make sense? So as Sam mentioned, you save a fortune in time, but it kills you in space and a number of gates. So here's an example. This is kind of hard to see, but there's no way I'm drawing this out. So this is what the logic for a 4-bit carry look-ahead adder looks like. Okay.
Yeah, we saw one
Okay.
yesterday.
Got it right here on those 74181.
So that's all well and good. Well, that's not too bad. The problem is that, as you can see, so here's the carry input, the carry look-ahead logic has one input. Here it has two inputs. Here it has three. Here it has three inputs. Here it has four inputs. So as we go up, we increase by one each time, right? So that means that it's going to be the summation of 1 to n, which goes as n squared, right? So our number of gates and inputs goes as n squared, which is bad. However, for low n, that's not so bad, right? If we have n equals 4, we can put the whole thing on this page. But usually we don't want to build 4-bit adders. Usually we'll want to build 16, 32, 64-bit adders. So this is a problem. Well, what we do then is we take this 4-bit adder, and when our data comes in, say our 64-bit number comes in, what we do is we'll split it up into 4-bit chunks. So that we'll use this for our 4-bit chunks, and then we'll do a ripple adder to add up the 16 partial sums that you have. Okay? So you no longer have to ripple through 64 stages to get your output. You only have to ripple through 16, which is a huge savings. Okay? Everybody cool with that?
Couldn't we apply a 4-bit adder again to the 16?
Couldn't you apply? Well, we break it up into 4-bit. I mean, we take a 64-bit number and break it up into
4-bit adders, 16 of them.
Yes.
And now we have 16 wires. Couldn't we arrange those into 4-bit adders?
You could, and that's that's a logarithmic. That's a logarithmic carry look-ahead adder, and they do that because it goes as the log of the number of bits. All right, last topic. You guys dead yet? Okay. I'm just glad I have you for the first one of the day instead of the last one. Yep.
So did you guys draw straws or something?
Well, there's things that I'm better at and things that he's better at. So.
You're better at the early one.
Yeah. Well.
Yeah, he's not awake yet.
Yeah. Fair enough. What?
I haven't written that down yet.
Okay. So we'll work over here. So, if we think about multiplication and implementing a multiplier in hardware, I mean, if we just think about it in general, it seems like just a huge task. But if we think about it a little closer, we know that if you multiply things, you're just doing a whole bunch of additions, right? And you say, well, maybe I can use that to my advantage. And as it turns out, the properties of binary multiplication make that even easier. So whereas the task of designing a multiplier at first seems horrendous, it's actually not that bad. And here's why. So let's first talk about binary multiplication. Okay? So let's do, in decimal we have 11 times 13. Okay, so it's 33, 1, 1, 143, right? Great. Everybody's happy. So,
That's all it takes. 11 by 30.
so let's now do it in binary. So we have 1, 0, 1, 1 times 1, 1, 0, 1. Okay? All right. So, multiply the 1 times that, we get 1, 1, 0, 1. Come over a space, multiply 0 times that, 0, 0, 0, 0. Multiply 1 times that, 1, 1, 0, 1. Multiply 1 times that, 1, 1, 0, 1. And add. 1, 1, 1, 1, 0, 0, 1.
Did you forget a carry? Yeah.
Yes, I did.
The second to the last on the left. No.
Yes. That's right.
Right, okay. Yeah.
Okay? So we look at this, we say, something about this looks like we might be able to use it for a multiplier. Let's look at it. Let's look at it just a slightly different way. Let's multiply the same thing out again. 1, 0, 1, 1, 1, 1, 0, 1. Okay? Now we can also view this as a bunch of, so basically what this is, so we have our multiplicand, our multiplicand, our multiplier, and then what are these? So this is this, this is 0, this is this shifted over, this is this shifted over even more. So the only thing we really have in our sum here is the multiplicand and 0. Well, so if we do that, then we can think of, so we start out with 0, 0, 0, 0. And this is going to be our partial product. Okay? So what we're going to then do is bring this, so we do the first multiplication, 1, 1, 0, 1, and add. So it's 1, 1, 0, 1, and we'll tack another 0 on just for fun. So then we do, so this is our first partial product, and this is our multiplicand. Okay? So then we do our next multiplication. So we don't put anything in here. I'll denote that with an arrow. So then we get 0, 0, 0, 0, right? So this is our partial product, and this is this is our multiplicand. Same thing. This is our shifted, basically our shifted multiplier. So then we do another sum, 1, 1, 0, 1, 0. Add another 0 for fun. So then we do our next one. We put our 2 arrows here. Then we get 1, 0, 1, 0, 1. Add 1, 1, 1, 0, 1, 1. Add a 0 for fun. And our last one, we bring down 3. And we multiply again. 1, 1, 0, 1. 1, 1, 1, 1, 0, 0, 0, 1. Same answer. Imagine that. So what we see that if we shift, so if we do a partial product and we add at each step and we keep track of this partial product as we go down, we've essentially done the multiplication, right? So all we have to do is shift over and then add. Shift over and add. Shift over and add. How do we do this? Well, let's draw a circuit. This is, I think, pretty much the simplest way to design a 4-bit multiplier. Where would be best for me to draw it? Right here? Is this okay? Not a particularly great layout for everyone, but you done with this, Gary?
Yeah.
That was fun. Why couldn't they put a whiteboard here?
We had a whiteboard.
What was the problem with it?
It's too small.
Big whiteboards. Yeah, okay.
He's a mathematician, they don't know why it works.
I guess. Okay, so before we start drawing this circuit, let's define something here. So we know what wires between two things look like. We know that this is a multiplexer, right? Now, if I draw this with a wire with a slash and a 4 through it, that means that this wire is 4 bits wide. Okay? Everybody get that? Now, I'm going to do a couple of funny things here that go along with this. What you can do is, if this is 4 wires, that actually means something like this, right? And what I'm going to do sometimes is, so this is 0, 1, 2, 3, right? What I'm occasionally going to do is I'm going to take this off somewhere else and use it. And I'm going to bring another one in here to replace it. Okay? So I'm going to peel off my least significant bit occasionally, and I'm going to add the most significant, so it's going to shift it down, right? So I'll explain that when it happens when I'm drawing here. So let's start out. Must be conservative with space. Okay, so we have x coming in and 0 coming in, okay? And y, 0. So what does this say? It says we're either going to choose x or 0, depending on whether y0 is 1 or 1. Oh, 1 or 0. So if y0 is 1, then we get x, which is this. Okay? If y0 is 0, then we get 0. So this is y0, and this is x. So this is basically our first multiplication, determining which one of those we want. Okay? So this is 4 bits. This is a 4-bit 0. Then we come down here, 4 bits. Here's where we're going to do the little trick. I'm going to split off the least significant bit and take the 3 more significant bits. Okay? And actually, let me condense this a little, or I'm going to run out of space. Okay, so I put my 3 in here, and this is going to be my 4-bit adder. Okay, so this is my first product, and then I start doing the same thing again. And I put in y1 this time, right? And I take my 4 bits and put them in here. Okay? So now I'm choosing. So now I have what I have is I have these 3 bits from my first term, right? Okay, because I peeled off the bottom one. And so these are now, it stays, basically I want to add a 0. So 3, and then I'll put another line here that's the 0. Okay, so we put a 0 on the end. In this case, it'll change as we go further down, right? Because we want to still keep this to be right here. We want to put a 0 there, so it still stays the most significant digit is still in the same place. Okay, then so now I want to add this. So I want to add this here to y1 times x. Okay? This represents basically y1 times x, right? So now I add those two, and then I get what I get out of there is my partial product. However, what I did here was I peeled off my least significant digit. So what I did here was I peeled off this digit. Okay? So I'm basically doing this sum right here. Okay? That's what that 4-bit adder is doing, is this sum right here. Okay? Now, next, I take my output of my 4-bit adder. I go ahead, I peel off another bit. This is Z1. And I come over here. And so I have 3 bits left here, right? I take my carry out from my 4-bit adder and make this. So this is 1, this is 3, this is 4. Okay? So now I have 4 bits here, right? So I draw, again, X, 0, Y, 2. Okay? And then we go into another 4-bit adder. This goes in here. This goes in here. So now we're doing this multiplication. So this is the sum we had from before, which is right here. And this is the result of y2 times x. Okay? Everybody got that? Yes? No? Okay.
Coming out of the first 4-bit adder,
Mhm.
the carry is the one on the side?
No, well, it's actually on this side.
On the output side of that.
This, yes, this
That's
is the
the
carry. This
carry.
is
Okay.
C out. Okay. So last time I promise. So we do our little black magic here. X for 0 for y3. Okay. So then this is 4. Now coming out of here, we peel off another bit. Z2. And then we bring the, actually, running out of space, come over here. We combine this 1, this 3, get a 4, right? Come in here, do our last add, and then we have out of here, we have Z3, Z4, Z5, Z6, and our carryout is our Z7.
Just for edification.
Yes, essentially.
It looks like a new problem set. So is this actually how it's implemented?
No, this is the simplest way. This is the easiest way. This is the most intuitive way to see it. When they, well, 30 years ago, when they implement it, they obfuscate it so much that you can't tell what the hell is going on. You know, you have to study it for a couple of weeks before you actually understand how the internals of the multiplier work. But this is basic multiplication. If you had to, you could go to Radio Shack, buy the parts, build a multiplier. Right? Any questions?
Can you buy 4-bit adders? Is that
Yeah.
Yeah. You just
Yep. I think you should be. I don't know if you can go into Radio Shack and buy them. I think you probably can't, but they definitely have them in the Radio Shack catalog. But you don't buy stuff from Radio Shack. You buy stuff from DigiKey. You get a big, thick book, has all the ICs in it you could possibly want. DigiKey, DIGIKEY. www.digikey.com. I expect my check. So, is there any questions? Any of the stuff we've done?
I'm a little bit curious about how the selector works there. Y0 comes in and basically it's a 1, we select X. If it's a 0, we select 0.
Mm-hmm.
Yeah, we did that on an exam.
That was, yeah, you had it on an exam.
Well, yeah, it was last month though, so I probably thought the question said, "Where's Georgia?" Oh, okay, okay.
So yeah, it's. I think we might do implementation. Basically how you do some lower level. Basically how we design an AND gate and an AND gate, an OR gate. We're gonna, I think, do that in terms of actual transistors, and we'll also do muxes and flip flops and all of that stuff. I think. If not, then next time I come in, I'll do it for you. But I think we're gonna cover it, and I think I'll be doing that recitation. So, anything else?